The cantilever beam of length L carries a uniformly distributed load of intensity WO, which includes the weight of the beam. Number 1, derive the equation of the elastic curve, and number 2, compute the maximum displacement if the beam is a W12 by 35 with L equal to 8 feet, WO equal to 400 pound per foot, and E equal to 29 times 10 to the 6th psi. For W12 by 35, the properties are the following. I is equal to 285 inches to the fourth, and S, or section modulus, is equal to 45.6 inches cubed. Now, this is the profile of the beam. We have fixed on one end and free on the other end, and it has a length L and a load WO. To derive the equation of the elastic curve, we use the formula for double integration. The formula is EI V double prime equals M, where E is the modulus of elasticity, I is the moment of inertia of the section, V is the value of the displacement, and M is the moment equation. To get the moment equation, we cut a portion of the beam here and then expose the internal forces, which is M and V, and this point is at a distance x from point of origin, which is this. So from this diagram, we can derive the moment equation. By summing up moments equal to 0. So we have M positive because it's counterclockwise, and then we get the resultant of this load. The resultant is WO times X, and it has a distance of X over 2. So this is plus because this is still in the counterclockwise direction. So WO X times a moment arm of X over 2 equals 0. Therefore, the moment is negative WO X squared over 2. Then we place this moment equation in this equation. So EI V double prime equals negative WO X squared over 2. Then, to solve this equation, we integrate twice. So integrating, we have EI, integral of V double prime is V prime, and integral of WO X squared over 2, this is similar to U to the N, wherein if you integrate U to the N, that will be equal to U to the N plus 1 over N plus 1. So therefore, the integral of this one is negative WO X to the N plus 1, N is 2, so this will be 3, and then over 3, but we have a denominator of 2, so 3 times 2, that will be 6, plus C1. Then, to get V, we integrate again. So, EIV equals negative WO X to the third, so U to the N again, so X to the 3 plus 1, X to the fourth over 4, but we have a denominator of 6, so that will be 6 times 4 or 24. And C1, this has an imaginary x to the 0, so that will be C1 x to the 0 plus 1, so x to the first power over 1. So simply C1x plus C2. And this is now your deflection equation. And this one is your slope equation. Now, our next task is to solve for C1 and C2. We can solve that one by using the boundary conditions. The boundary conditions are at x equals L, the slope or V prime equals 0. And at x equals L, V or the deflection is also equal to 0. Now why is that? Because if we look at this beam, the elastic curve is in this shape. Alright, so here we have a 0 slope. Hence, V prime equals 0. X equals 0, x equals L. So at x equals L, the slope of the elastic curve is 0. And at x equals L at this point, the deflection is 0. Why? Because this one is a fixed end. And fixed end don't deflect. So therefore, V is equal to 0. Now using these boundary conditions, we can now solve for C1 and C2. Let's bring this equation down and substitute the values. So here we have EI and substitute the values. That is equal to negative WO x cubed. So negative WO, x is L. So L cubed over 6 plus C1. This is 0. So we now have WO L cubed over 6 plus C1 equals 0. Hence, C1 is equal to WO L cubed over 6. And then, using the deflection equation, we can solve for C2. Substituting the values of the boundary conditions, we have EI times V, which is 0, that is equal to negative WO x to the 4th over 24. So negative WO x will be substituted with L to the 4th over 24 plus C1x. But C1 is already solved. C1 is WOL cubed. Sorry, I didn't notice that the camera was turned off. So we were here. WOL cubed over 6. This is C1 times x. X is L plus C2. Now, L cubed times L is L to the 4th, and 1/6 is also equal to 4 over 24. We are doing this so that we can combine these two like terms. Now we have WOL to the 4th, then WOL to the 4th. So the answer will be, if we combine these two terms, we have WOL to the 4th, and the coefficient is negative 1 over 24 plus 4 over 24. That will be positive 3 over 24 or 1 over 8. So we have 1/8 WOL to the 4th plus C2. And that is equal to 0 because this one is 0. So therefore, C2 is negative WOL to the 4th over 8. Then, because we were already able to solve C1 and C2, we are now ready to substitute to this equation so that we can get the final deflection equation. So for the final deflection equation, EI V equals negative WO L to the fourth over 24 plus C1 X. So C1 is WO L cubed over 6 times X plus C2. Plus C2 is negative WO L to the fourth over 8. Now here, we can factor out WO and 24 to make the equation simpler. So WO over 24 times negative, this is X to the fourth. So we have X to the fourth. Then we have extracted WO already, so this will be L cubed plus L cubed, and then 1/6 will also be equal to 4 over 24. So we have, if we extract the 24, we have 4L cubed times X minus L to the fourth over 8. Now, 1/8 is also equal to 3 over 24. So therefore, we have 3L to the fourth. And this is now the final equation. Now for question number 2, compute the maximum displacement if the beam is a W12 by 35 with L equal to 8, WO equal to 400 pound per foot, and E equal to 29,000 or 29 times 10 to the 6th PSI. So in here, we simply use this equation. But if we look at the elastic curve, we know that the maximum deflection or displacement is located at, so at x equals 0, V is maximum. And since we are looking for the maximum displacement, we simply use this equation and substitute the value of x, which is 0. So using this equation, we substitute the values. E equals 29 times 10 to the 6th. So 29 times 10 to the 6th. Then I is 285 inches to the 4th. So 285 times V, which is unknown. And that is equal to WO. WO is 400 pound per foot. But remember, our equation should be in terms of inches. So 400 pound per foot, converting it to inches, that will be 1 foot over 12 inches. You cancel the foot, so you get 400 over 12 pound per inch. So that will be 400 over 12 over 24. And then multiplied by x, but x is 0. At x is 0. So negative 0 to the 4th, which is practically 0, plus 4 times L, which is 8 feet. And 8 feet is, to convert it to inches, we have to multiply it by 12. Cube. And then x, but x is 0 again. So that will be practically 0 minus 3 times L to the 4th times 8 times 12 to make it inches to the 4th. So here we have one equation, one unknown. The only unknown is V. So we can solve for the value of V, or the displacement. And using your calculator, you'll be able to get a value of negative 0.0428 inches. The negative sign here means that the deflection is directed downwards. Lastly, to be able to visualize the behavior of the moment and stresses, we also need, I feel that we need to compute also for the maximum stress. Now, the maximum stress occurs at the maximum moment. So, at x equals L, at this point, we see that this is the maximum moment by inspection. M is maximum. And we know that stress is equal to mc over I, or equal also to m over s, where s is the section modulus. And m is the moment equation, and the moment equation is here. Negative WO x squared over 2. So bringing that one here, that will be using the absolute value, WO x squared, but we substitute x with L, since x is L at this point. We are looking for the moment at this point, so that will be L squared over 2, and then we have the denominator S. So substituting the values, WO is 400, but we convert it into pound per inch, so divided by 12, times L squared, we have 8 squared over 2, and S is given as 45.6. Simplifying that, we get the value of the stress equal to 33,700 psi. Thank you for watching.